to the defined cross-section, which is the opposite, exactly opposite of what you are assuming in the 1D approach. In practical terms, what this means is that the model will not give you accurate results in this kind of situations, and it requires some more sophisticated models such as the two-dimensional approach. Next slide shows a representation of a terrain as you can get with the RiverFlow2D model or other other two-dimensional models. You see on the left you have an actual terrain surface, and this is something that you can work very well with InfraWorks 360. Then on the right you have a flexible mesh, which is the base mesh of the RiverFlow2D model that is formed by triangles of different size. So when you represent this three-dimensional surface or terrain, which is maybe very complex, as you can see there, with the two-dimensional mesh, the two-dimensional model is able to capture the actual terrain in a much better way than it can be done with a 1D approach. And other things, next slide, shows also that the mesh can adapt to obstacles that you can have in the floodplain. As in an urban area, you can have buildings, streets, and so the mesh is able to determine all these obstacles that may occur, and the base element for computation that the model uses is the triangle, and in each triangle the velocity can have not a single direction, not 8 directions, but any direction that can occur in that particular area. And the model computes not only the velocity but also the depth of flow, obviously, and that allows you to have and generate maps of the flooding situation, not only for a single time but also for throughout the flooding event. So just to give you a little history, a little more than expand a little on what Charlie presented. We started, Hydronia started a collaboration with Autodesk back in 2014, and it's still going on. We started with an initial version of the flood simulation plugin for InfraWorks in the Autodesk Labs environment. There was Project Boulder that was graduated in September of this year, just a couple months ago, and it has gone commercial since then as a plugin for InfraWorks 360. Now, I need to tell you, next slide shows a little graphically what's the relationship between the RiverFlow2D full product with respect to flood simulation for InfraWorks that has been implemented so far. What we have now within the InfraWorks environment is just tip of the iceberg. We have a number of features that are available that potentially can be incorporated into the flood simulation plugin for InfraWorks. Now, the RiverFlow2D is actually a combined hydrologic and hydraulic model. So it deals with rainfall, evaporation, infiltration, but also with the flow routing. It uses flexible mesh. It can deal with dry and wet areas, supercritical, subcritical flows. It can have internal structures as culverts, weirs, bridges, and other two-dimensional structures that exist in the floodplain. You can have additional add-on modules for erosion deposition, water quality, mud and debris flow. It works in English and metric units, and it has a GPU high performance option that can run even 150 times faster than the standard CPU version. The next slide shows a little details of the hydraulic structures that are included in the model. We can have internal rating tables, sources and sinks, so you can have an intake, for instance, or some other type of sink that goes into storm water sewer or something like that. Bridges in 2D, the bridges can be of any alignment with respect to the flow. You can model overtopping, pressure flow in the bridge. We have a gates component that can model how a gate structure performs during the simulation, culverts, and also weirs that are useful sometimes for modeling levees and sound walls or some other kind of structure. The next slide shows the hydrologic components. As I mentioned, we have a rainfall operation. Rainfall can vary in space and time. And also the infiltration can vary in space and time, but also can use different methods that you can use in different areas like Horton, Green Amp, or curve number to determine the infiltration losses. Briefly, I will show you some results of the model. The model can do very small areas, but it can also handle extremely large areas, even statewide areas. We have very large applications of the RiverFlow2D model that encompasses entire states, like in Tasmania, for instance, in Australia. The model has been implemented in 350 watersheds. It's a single model that handles the whole state at once. And also in the United States, we have, for instance, the Red River of the North, 420 river miles that has been implemented by NOAA. And this is a forecast, river forecast model, and that has been tested. What you see on the left are watermarks sites that have been recorded to check the model results. And in the next slide, I'm showing a comparison of the model results with the actual field data along these 420 river miles. And what is interesting about this particular application is that the two-dimensional implementation of the model using the GPU acceleration technology is able to perform even faster than the 1D model that NOAA had implemented previously. And this is due to the parallelization techniques that are used in the model with the GPU version. Next slide, just to summarize some of the advantages of the RiverFlow2D for InfraWorks. It's a super stable computational engine. It almost never crashes, if you could say that way. It preserves water volume exactly, so it conserves the actual volume of water, which is an issue in some other models. It can handle water flow over any terrain, even vertical walls. And it has the potential to grow in capabilities because we have many other features in the RiverFlow2D model that actually some of them are being implemented as we speak and will become available in future versions. It has a seamless integration with InfraWorks 360 graphical interface, and this has been an amazing work of an Autodesk development team that they have been able to do this seamless integration with this plugin, and it's actually a pleasure to work and develop these flooding simulations. The model, as I said, is very fast, and it's much faster than all models. Just to give you a quick comparison, the next slide shows a graph of one of the UK benchmark tests that deals with a 780 cell mesh, and I'm comparing here the times, simulation times in hours between HEC-RAS2D and RiverFlow2D using a GPU Titan Black card. And in this particular case, the RiverFlow2D model performs about 24 times faster than the equivalent model with the same mesh HEC-RAS model. So just to finalize, some of the application areas where you can use the RiverFlow2D flooding plugin for InfraWorks. For instance, general two-dimensional river hydraulic simulations, where you are interested in just modeling river reach, interaction with floodplain, dam break flood analysis, something you could do also to see how the flood progresses in downstream from a breach on a dam, floodplain risk assessments, also coastal and urban flooding, which is a very important application for sea level rise, storm surges, hurricanes, effects on urban communities. And also, I think that the integration with RiverFlow2D and InfraWorks, you will get a better picture of that in the demonstration that Charlie will do just now. So with that, I'm happy to send Charlie the control of this that will show you some demonstrations of how the flood simulation works.
Okay, thank you, Ronaldo. All right, so I'm going to go through and show some examples how we can set up a flood simulation in InfraWorks and show a few different scenarios. So first off, let me just describe the process. We start with a terrain inside InfraWorks. This could be, my examples are basically going to be model builder. It could be some DEM data to start with, so you get kind of a larger area, and then supplement that maybe with more detailed terrain. If you have Civil 3D surfaces for specific project area, you can include that into InfraWorks. You may also want to include bathymetry, bottom of the riverbed, type of data for more accurate results. Most of the DEM and model builder data, you'll see the water surfaces are actually modeled as terrain. So you'd really, for a more accurate model, you'd want to include kind of the bottom of the water surface elevation. The examples I'm going to do are large historical flooding events, 10 times or so larger than the average flow, so it minimizes the error there, but that larger difference. But the first step in the workflow is to then go and define the flood simulation area. So we just outline the area inside our model. You really want this to encompass all parts of the flooding from where the water comes in to goes out. You kind of want to avoid water spilling out the edge. So leave enough buffer around the area that you're trying to analyze. Then what we'll do, along the boundary, you'll define where water comes into the boundary area. This is our inflow area, as well as where water goes out for your outflow. And then in the panel, just define some of the conditions for inflow and outflow, settings for the simulation, and then you'll go and run the simulation. This will send the terrain, the boundary, all the data to RiverFlow2D, the calculation engine. It'll compute the simulation in the background, and then the results will be returned to InfraWorks, and we'll be able to view those in our model. You'll be able to play an animation showing the flood depths, elevations, or velocities inside your InfraWorks model. So I'm going to first just demonstrate this with a simple example. This is our office building in Manchester, New Hampshire for Autodesk, and 10 years ago or so the Merrimack River that flows next to the building flooded into the parking lot area here. So I'm going to simulate this with the flows from that event. So just to show an example of how to set this up inside InfraWorks. So here's my InfraWorks model. You can see the office building and the river that flows next to it. And on the drainage toolbar, under analysis, you'll find when you have the RiverFlow2D plugin installed, these two commands down at the bottom, flood simulation and this flood snapshot. So flood simulation will let me define my simulation area, set up the configuration. So all I'm going to do here is just outline my area. Just trace over where I know the flood isn't quite getting this far off. And double click to complete the boundary, and then define where the inflow area is. And I'm just going to pick 2 points. The water's flowing left to right here. Left is actually north. And then define my, whoops, I should have. Okay, now define my outflow area. I'll point out what that was just prompting me for in a moment. But my inflow, my outflow is to the right. So the area is defined. Now I just need to fill in some values for my inflow. So I'm just going to enter a static flow based on the event here. And I'll talk about some of the outflow conditions later. The settings, this just controls, so this is going to push the terrain to RiverFlow2D based on the triangle size that's entered here. Manning's value can either be a uniform roughness over the entire area, or you can see mine set to distributed. I'll talk about this in a moment, but this basically is using some coverage areas that are in my model. Manning's values can be assigned to the coverage material, and that way you can use different roughness within the area. And then just to set up, I think I only need an hour here, and an interval. So this just sets up how long the simulation spans in the interval. If you use a larger time and a smaller increment, the calculation may take longer, but may give you some different results. So you may want to play around with those settings. But I'm going to run this simulation. It's sending the data to RiverFlow2D. You can see down the bottom that's opened up. You don't need to open this up to look at it, but this does give you the progress of what's happening in the calculation engine. So you can see it's spanning the hour that I entered. And when this is done, we'll have our results that we can show in the model. So it's just showing us the progress here, and then a new panel will open up when it's done. And from that panel, just open up over here. Just move it kind of out of the way, but where we can see it, here we can animate the results. So we have a few theme options. I'll just start with water surface elevation. What this will do is it colors the water along the flood so that we can see the higher elevation values are in the red color down to the lower elevations in green. The depth animation, this will just have different highlights of blue showing how deep or shallow the water is. And I'm just going to pause it when it gets to the state here where we can, I'm just zooming into where the office is, and you can see it's flooding up into the parking lot. This is one case where the terrain is important for how accurate the flood is going to look like, especially at the outer edge. My terrain isn't quite modeling what, if you've been to our office here, this is pretty steep tiered parking lots, parking levels. But the result is pretty close to, the water actually flowed up into the front of the building here. And the third theme is velocities, and actually with each of these, we can also turn on velocity arrows. I'm just going to play this simulation. So this is showing in orange the faster velocities, and in green are the slower velocities. With any of these themes, if you want to save this display for later, you can use this Create Snapshot button. And that way, when we get out of the flood simulation tools and you're working on your model, maybe designing part of a site here, you can come in and turn on the flood snapshot, and that'll bring back the display so you can see the extents of the resulting flood. All right, so that was just a quick example how to set up a basic model, and this model was, the terrain is basically, actually this one was a DEM, but my other examples are just from Model Builder. So I'm going to jump into a little more detail in the workflow. One thing I mentioned was the distributed roughness or distributed bandings value. This helps you create a more accurate model, since there are different materials along the riverbank, along the floodplain area, or the floodway, and these different materials have different bandings values, and those control how water flows over the surface. So a simple way, if you're not sure and you're early, you can just use the consistent value, or you can set it up to use distributed bandings value. And we do this by creating those coverages that I showed. You can create a coverage area just where a different material is represented, and then the coverage has a material style, and then we map that style to a bandings value. The mapping is done in a file that's located here. I'm showing the path, the name of the file. You can open this up with the text editor. It's just an ASCII file, so you can use Notepad, open this up, and edit it. It may look a little intimidating, but there's really not much to this. It's just simply a number of lines, and I'll show you the file in a minute. But it has the name of the material, default runoff coefficient, and a default or Manning's coefficient. So the runoff coefficient is here because originally this was used for the pavement drainage commands in InfraWorks. So if you're analyzing or doing pipe sizing or spacing inlets along a road, it's looking at the runoff coefficient of the materials on the road components. But for flood simulation, it's using those same materials, but just going to use the Manning's coefficient that's entered here. So an example of this, the material just gets changed to basically the path and the name of the material style, and then you put in the values for runoff coefficient and Manning's. So I'll jump back over here. Actually, let me open up first that path. So the path that I showed here, you'll find that mapping file. And in here, you'll see there's a long list of different materials that are all mapped to runoff and Mannix values. So a lot of the out-of-the-box materials are already in this list, but you may often create your own material, and what you'd want to do is then map that appropriately. So all you need to do, there's a space at the bottom to put in your own user-defined mappings, just to keep them separate from the out-of-the-box ones. And if you just copy this line, and paste it, and remove the semicolon at the beginning, then all you need to do is just put in the name of the style. So just like the ones above it, most of them are in this material folder, and then a different folder on the style palette, and then the name, and enter your coefficient values. And then just save this file and it would be ready to use. So let me go back to InfraWorks here and just point out, right, if you're not familiar, if I open up the style palette, rendering, what happened? My video card just crashed. All right, so I will open up InfraWorks again.
While you're rebooting, Charlie, there's a question here that I'm not quite sure how to answer. Do you know if users can create flood snapshots in multiple proposals in the same model?
I believe that you can, yes. Actually, I'd have to check that out, but I'm pretty sure that it...
Cool. I'm going to test it myself and see if I can respond to this.
Yeah, and I think, though, actually, let me clear. So you could have a different proposal and run a simulation, though. I think, actually, let me step back on that, because I think the model right now will just have one results file for the model.
Gotcha. Okay, cool. Well, thanks for answering that question, and I'll let you get back to what you were doing.
All right, so let me, while that's launching back up, let me just go back to PowerPoint. I was just going to show the coverage areas, where they are on the style palette, but let me jump forward here to a couple of the other features I wanted to dive into. In the original release, you could only have one inflow area, which makes it difficult to model, say, a river that has branches, like this one here, which is Troy, New York area near Albany, the Hudson River flowing down along the right, and the Mohawk River. These are both two fairly equally sized rivers, so you couldn't easily model this with one inflow area. So a new feature in the coming release is to be able to define multiple inflow areas. So we can define them separately by clicking on our boundary, and then provide different inflow conditions for each of those. Also, in my simple example, I just showed a fixed flow rate, but what we can also use or import a hydrograph or discharge versus time file that will vary the flow over time. You can create your own file for this. It's just a very simple text file that you can create in Notepad. It's a series of time versus flow, time in hours. You can use decimals, even though I'm not showing, these are all, I'm just showing whole numbers, but you can use decimals instead. The flow value is either in cubic feet per second or cubic meters per second, and you'll specify that in the flood simulation tool. One caveat is you need to have the first row represent how many data entry points there are. So 6 for my 6 events that I've entered here. Another inflow condition that's in the new, will be in the new version, is elevation versus time. This uses a very similar file, exact same setup, it's just hours versus elevation data, which can be either in feet or in meters. But again, the number of events is entered up at the top. So this could be very important if you're modeling, in many cases, rivers. I found, in some cases you can find historical flow data, but in many cases you have some either stage or elevation historical data for the river and maybe no flow. So to be able to model those rivers with that historical data, which is probably easier to record, you can use this elevation versus time inflow condition. Another case is modeling coastal storm surges. In the past, this would be kind of difficult with just the flow value because you don't really know what the flow is that's surging, whereas you have a better idea, or at least on historical data or the elevation that you're trying to model in your scenario. So it's easier to get to that elevation data. So that can be used both for river cases and also coastal storms. So let me jump back in here to InfraWorks and just show a few parts to this. Again, for the Mannings, I have some coverages defined here, and if you look over on the stack, you can see the style that my coverage is using. This one I created. It's for existing pavement. I made it clear because I just wanted to see the model underneath, but technically it's a style in the style palette. So you'll find it mixed in with your other materials. I have it here, so this would be what I'd want to map in that mapping file, and then just give it the appropriate Manning's roughness. And I'm going to switch models here. All right. Actually, I think I hit the wrong one, but this will work too. All right, I'll show this one first because it still uses both of those features that I talked about. So this is a model of Manhattan, and what I was going to model here is a storm surge from Hurricane Sandy, but can also model the flow in the Hudson River coming down along the west here. So what I'm going to do is set up a flood simulation, and you can see here before I do it, just a preview of what I'm going to do. Move this out of the way. So I have one inflow area coming from the coast, coming from, the ocean, and another inflow area coming down from the Hudson. And then my outflow area is actually going to be this, basically uptown and including the East River, because that connects back to the ocean and just allowing free flow there. So let me come in here, and I'm just going to do a new simulation, just recreate this to show how this is done. So again, I'm just defining my simulation area. And then defining the inflow, and in this case I have 2. So what it's prompting me down at the bottom is to double click if I'm finished with inflows. But in this case I'm not, so I'm just going to single click for my first one then draw the second inflow and double click on this one because I only want those two inflows. So now the prompt is asking me for the outflow. So it was a little different than what I did in the first case, or what I tried to do. So now I'm just defining the outflow area. Just a single click to end that, and it opens up the panel again. And then here I'll define my inflows and the outflow. So with the inflows in this case, instead of using the static flow, I'm going to use the discharge versus time and the elevation versus time. So you'll see under inflows, I have two inflows here, and when I select them, you'll see they get highlighted in orange for which the current one is. You can also pick them graphically here. Whoops. I picked shape. So we can switch between the two inflows, and for this one, the storm surge, I'm going to use elevation versus time. This is where you'd set the units of your file and then go and select the file that you have. So I have this text file, sandy elevations, and you can see it's just set up with time in hours and the elevation values. I spanned it over 27 hours to kind of mimic the surge from Sandy, and you can see the peak elevation at elevation 14. I'll switch to the Hudson River, and instead of static, I'm going to use discharge versus time in cubic feet per second, and then go and select the file I have for that. So I set this one up to use the same time span. I just varied the flow rate over time, so you can see that varies instead of using a static flow here. For the outflow, we can either use uniform, or I'm going to set it to free flow, but in some cases, like in a river scenario, you might use a uniform case where it will use the slope at the outlet end to control how water's flowing out of the area. You can either use user-defined and directly enter the slope value, or let the model calculate the average at that outlet. In this case, my outflow is Upper Manhattan and the East River. I'm also going to set see my triangles here. In this case, use a larger triangle area just because it's a larger model. And I also want to make sure that I span at least the time of my hydrograph files that I have. And I might set this interval at a higher value. And then I'd go and run the simulation. Okay, I don't want to actually, this will take 10 minutes or so to run, so we don't have that much time left here. So what I'm going to do is just open up a copy of this model that I have, and I can show you the results. So this is just the same exact model. I ran the simulation in it earlier. That's what you saw when I started off in this model. And let me just zoom in so you can see good vantage point. Go back to flood simulation. So you can see it's you can see the inflow area, the boundary, my outflows in the background, how I had set it up. I actually used a 200-foot triangle size, 36 hours and a 30-minute interval. But it's already been simulated, so you can reopen the model later once it's been simulated and always play the animation. So I'm just going to go ahead and play this, starting with water surface elevations, so you can see the peak of the storm surge. So the higher elevations in the themes are red. So when it gets to the red color, that's that peak 14-foot storm surge.
While we're waiting for this to load, I have another question for you and Reynaldo, Charlie, see if we can answer this. How can IDF curve data be transformed to Q values? Do we have any answers to that question?
Well, so I mean, the rational method, you can, the IDF curve is just part of the equation. You'd need the area of the tributary area and some runoff coefficient, and from that you could compute what the actual flow would be.
Awesome. Thanks for answering that on the fly. That wasn't an easy one.
So here we're showing, you can see the yellow and orange are kind of the lower elevations, and now the peak is coming in, and I'm just going to pause it there. So you can see the maximum extents here through the simulation. And I could create a snapshot, so we can always have this later in our model. Of course, we could also show depth, show velocities as well. All right, so I'm just going to jump back to the presentation here. So this was just an example. This is how I set up the model. So I had the surge coming in the lower left there, using elevation versus time, the Hudson River using flow versus time, and then a free outflow. The free allows water in and out, and that free outflow. But you can see the results over on the left compared to results USGS had presented, and pretty similar results, even though my model is purely from Model Builder. It's just a very simple terrain. But you can see the similar outlines resulting from this simulation. So what's next? I just wanted to post this. I think Reynaldo pointed out that there's a number of features inside RiverFlow2D that we could enable to use through the InfraWorks flood simulation feature. So a great place to tell us about that would be the InfraWorks 360 ideas page. If you haven't posted anything there, the link's right here. But the product teams use this as a way to gauge the importance of what the community is saying is important for us to include as features. So you're able to post something here, and then everybody else in the community can go ahead and vote for your idea or add their own ideas. So the product teams look at this. We may post some questions for additional information every once in a while, but this would be a great place to post what you'd like to see next for flood simulation. So with that, that's the end of my presentation, and I don't know if Eric is back.
So Eric's connection is a little patchy. He asked me to just wrap up by reminding everyone that our next webcast on December 21st will be about creating a virtual reality experience from an InfraWorks 360 model in minutes. And you can register for that the same way that you have for this current webcast, which is through our community site, our forum, Facebook, Twitter, or a LinkedIn group for InfraWorks. You should also receive the link hopefully by email if you've registered for a webcast before. And since we have 2 minutes left, wondering if you guys can answer a couple more questions. Or just one more question we have here. Can the results be exported by time? So can the border of a flooded area at every hour or water surface be exported as triangulation? Any thoughts there, Charlie and Reynaldo?
So not directly from like the InfraWorks model that we have, but Ronaldo, you might be able to talk a little bit about from the results file that's in the background. Maybe we can do something there.
Yes, actually in the background, the model outputs a number of result files, and that includes for every report interval, you will have the full triangulation with all the results that are available. So you can reconstruct with that file, and those are open format ASCII files that you can, you know, we document all the format and details that, and they are text files, so it's very easy to recreate the model results for every time after the simulation.
Great, thank you. So I just put up a slide here just in our last minute where you can check out where some of these links are to register for our next webcast. And if you want to repost a copy of this current webcast for your coworkers and colleagues, the recording will be published online on our community site, hopefully by the end of the day, possibly within a couple of days, so you can rewatch or pass it along to your friends. And with that, I think we'll end the session. Thanks again to Charlie and Reynaldo for sharing all of this knowledge with us. I hope everyone has a great day.
Thank you.